Enceladus. You're standing at a mission console inside the Jet Propulsion Laboratory in Pasadena, California. It is October 14th, 2015. The data is coming in live. You are watching it happen in real time. Numbers are scrolling. Flags are triggering. Something is wrong. Something is impossibly right. A moon of Saturn, a moon smaller than the United Kingdom, smaller than France, smaller than the state of Texas, is venting water into space. Not vapor traces, not frozen wisps, columns, geysers, erupting at over 1,400 kilometers per hour from a world with almost no gravity to hold anything back. The plumes are crossing into open space, and the spacecraft flying through them is tasting what's inside. The data is still coming, and every new line of it is changing what we thought we knew. Here is what Enceladus looked like before Cassini arrived. It was a small, icy moon orbiting Saturn at a distance of roughly 238,000 kilometers from the planet's center. Its diameter is approximately 504 kilometers. At that size, it should be geologically inert, a frozen remnant, cold all the way through, unremarkable except for the fact that it reflects sunlight with unusual brilliance. Its surface temperature reads at about negative 198 degrees Celsius in the sunlit regions. In the shadows, it is colder still. Nothing about those numbers should suggest a living world. Nothing about those numbers should suggest what the Cassini-Huygens spacecraft, a joint mission from the National Aeronautics and Space Administration, the European Space Agency, and the Italian Space Agency, was about to find. Cassini first detected anomalous heat signatures emanating from Enceladus's south pole in 2005. The South Pole should have been the coldest region on the moon. Instead, it was the warmest. Tiger stripe fractures, 4 parallel linear fissures, each approximately 130 kilometers long and roughly 2 kilometers wide, were venting material at temperatures approaching minus 93 degrees Celsius locally, a difference of more than 100 degrees compared to the surrounding terrain. That difference, on a moon that small, is not a weather event. That is a geological statement. Something was generating heat from within. Between 2008 and 2015, Cassini made multiple close passes through the plumes erupting from those tiger stripes, dipping as low as 49 kilometers above the surface. The ion and neutral mass spectrometer and the cosmic dust analyzer aboard the spacecraft sampled what was inside. What they found has been documented in a series of peer-reviewed papers published in the journal Science and in Nature Astronomy. The lead researchers include Hunter Waite of the Southwest Research Institute, whose 2017 paper in Science confirmed the presence of molecular hydrogen in the plumes at concentrations between 0.4 and 1.4% by number density. That hydrogen, the paper concluded, was most consistent with ongoing hydrothermal reactions between hot water and rock on the ocean floor, the same serpentinization process that drives hydrothermal vent systems in Earth's deep oceans. But the inventory did not stop at molecular hydrogen. Silica nanoparticles were detected, particles that form only when water at temperatures exceeding 90 degrees Celsius interacts with silicate rock at specific pressure conditions, then rapidly cools. Their presence means liquid water has been in sustained contact with a rocky seafloor. Complex organic compounds with molecular masses above 200 atomic mass units were confirmed in a 2018 paper in Nature by Frank Postberg of Freie Universität Berlin and colleagues. These are not simple hydrocarbons. These are large, structured carbon molecules of the kind associated with biological and pre-biological chemistry. And in 2023, phosphorus, one of the 6 essential elements for life as we understand it, was confirmed in the plume material by Waite's team, completing what astrobiologists call the complete chemical inventory of life: water, energy, organic chemistry, the precise minerals, the precise elements, all of it flying freely into space from a moon you could drive across in a long afternoon. The standard cosmological model for small icy moons says that bodies of Enceladus's mass should have lost their internal heat billions of years ago. The tidal flexing generated by Saturn's gravitational pull is real and measurable, but the models have consistently struggled to produce enough energy to sustain a liquid ocean across geological timescales, let alone one with active hydrothermal venting. The explanation of tidal heating is the consensus, and it is reasonable. It is the best framework available, but the data keeps exceeding the framework. The heat output from Enceladus's south pole has been measured at approximately 15.8 gigawatts, roughly equivalent to the output of 15 large nuclear power plants, sustained continuously, from a moon that small. Some astrophysicists suggest the tidal dissipation models may be fundamentally underestimating the internal friction within Enceladus's silicate core. A minority of researchers propose that the moon's interior has not been adequately modeled, and that the actual hydrothermal system may be older and more extensive than current simulations allow. What is living in that ocean? What has had time to begin in the 4.5 billion years that system has existed? If hydrothermal vents on the floor of that buried sea are as chemically rich as the plumes suggest, is anything consuming that hydrogen? And if Enceladus can sustain all of this, in a solar system most people have never thought of as a candidate for life, how many other moons in this solar system alone are we ignoring? The answer to that last question begins roughly 628 million kilometers from Saturn, orbiting Jupiter, where a world the size of our own moon has been hiding an ocean beneath its ice for longer than complex life has existed on Earth. Europa. You're looking at the wrong thing. That's what the scientists kept telling themselves in the winter of 1979, hunched over grainy black and white images returning from Voyager 2 as it swung through the Jovian system and kept moving, indifferent, already aimed at Saturn. Everyone wanted to look at Jupiter, at the storm, at the scale of it, a planet so large that 1,300 Earths could fit inside it with room to spare. But the scientists who stopped and looked at the little moon, the one that shouldn't have been interesting, those were the ones who went quiet. Because Europa's surface had no craters. Worlds collect craters. That's what they do. Every dead, frozen body in the outer solar system is pocked and scarred from 4 billion years of bombardment. But Europa looked young, smooth, almost unmarked, and cut across its pale surface in every direction, like something had cracked it from below, were lines. Thousands of them, red-brown and deep, not geological formations anyone had seen before, not impact scars, not volcanic ridges. Something underneath had moved. The Galileo spacecraft arrived at Jupiter in December of 1995 and spent 8 years making repeated flybys of the Galilean moons, including 36 dedicated passes over Europa. What it returned changed the way planetary scientists think about where life can exist. The mission was managed by the Jet Propulsion Laboratory and produced findings that were published across dozens of peer-reviewed papers in the journal Icarus, UNIN, Nature, and in the Journal of Geophysical Research. Throughout the late 1990s and early 2000s, here is what the data showed. Beneath a shell of water ice, estimated to be between 15 and 25 kilometers thick, Europa contains a global liquid ocean, not a pocket of slush, not a subsurface lake the way Antarctica has subglacial lakes. A world-encircling ocean of liquid salt water, kept in motion, kept warm enough to remain liquid not by the sun, which at 628 million kilometers from Europa delivers only about 3 to 4 watts of energy per square meter, compared to 1,361 watts per square meter at Earth, but by something else entirely. By gravity. By the relentless tidal kneading of Europa's interior as Jupiter's enormous gravitational field pulls and compresses and releases the moon with every orbit, generating frictional heat from the inside out. The volume of that ocean is estimated at 3 times 10 to the 18th power cubic meters. To make that feel real, every ocean on Earth combined, the Pacific, the Atlantic, the Indian, the Arctic, all of it, contains approximately 1.335 billion cubic kilometers of water. Europa's ocean contains roughly twice that, twice the water of every ocean on Earth, wrapped inside a moon that is only about 3,100 kilometers in diameter, sitting in the frozen dark 600 million kilometers from the nearest star. The standard cosmological model, or rather, the standard model of habitability, says life requires proximity to a star. The classical habitable zone, defined by researchers including James Casting of Pennsylvania State University in his foundational 1993 paper in Icarus, describes the orbital band around a star where liquid water can exist on a planetary surface. Europa sits nowhere near that band. By every classical metric, Europa should be a frozen rock. The mainstream scientific consensus has updated significantly since Galileo. The revised framework accepts that tidal heating can substitute for stellar radiation as an energy source, and that liquid water beneath an ice shell can in theory persist for billions of years. The European Space Agency's Jupiter Icy Moons Explorer mission, launched in April of 2023, is en route to the Jovian system, with specific instruments designed to characterize Europa's ocean depth, salinity, and ice shell thickness. The National Aeronautics and Space Administration's Europa Clipper spacecraft, launched in October of 2024, carries 9 scientific instruments and will conduct approximately 50 flybys of Europa beginning in 2030. Measuring the ocean's chemistry and mapping its surface with radar capable of penetrating the ice shell. The scientific community has arrived at something close to consensus. The ocean is real, it is salty, and it has been there for a very long time. But here is where the model strains. Europa's surface shows clear evidence of what planetary geologists call chaos terrain, regions where plates of ice have fractured, drifted laterally, rotated, and refrozen in new positions, like a broken and re-iced Arctic Sea. Researchers including Brittany Schmidt of Georgia Institute of Technology, writing in 2011, proposed that this surface behavior requires liquid water to exist not only deep in the ocean, but at relatively shallow depths beneath the ice shell, possibly within a few kilometers of the surface. Some astrophysicists suggest this means Europa's ice shell is actively cycling material between the surface and the ocean, that compounds formed on the irradiated surface, including oxidants and potentially organic molecules deposited by comet impacts, are being carried downward into a warm, dark, chemically rich ocean. The model can explain a static ocean, it struggles to explain a dynamic one. What is living, if anything, in that darkness? If Europa's ocean floor contains hydrothermal vents, and the tidal heating that warms the ocean makes this plausible, what has had 2 to 3 billion years to evolve around them? If material is cycling between the surface and the deep, is the chemistry of that ocean being continuously refreshed? And if Europa Clipper finds complex organic molecules in the plumes that some researchers believe vent from Europa's surface, what exactly are we prepared to conclude? Titan carries a different kind of ocean, one that never touches water at all, and what it might mean for life is stranger still. Titan. You're not looking at a planet, you're looking at a moon. But your instruments don't care about that distinction, and right now, hovering inside the data stream from the Cassini-Huygens mission's final atmospheric pass on September 14, 2017, neither do you. The orange haze fills your screen, dense, layered. Nitrogen and methane braided into a sky so thick with chemistry that Titan blocks more sunlight than clouds do on Earth. You're watching a world that is simultaneously doing 2 completely different things to support life. One at its surface, one 100 kilometers beneath it, and the universe has said nothing about which one matters more. This is not metaphor, this is the data. Titan is Saturn's largest moon, the second largest moon in the entire solar system, measuring 5,150 kilometers across, larger than the planet Mercury. It orbits Saturn at a distance of 1.2 million kilometers, completing one orbit every 15.9 Earth days. Its surface temperature sits at approximately 94 Kelvin, which is 179 degrees below 0 Celsius. At that temperature, water is not a liquid. Water is rock. Water is geology. And yet Titan has lakes. It has rivers. It has rain, seasonal flooding, coastlines, deltas, and drainage basins that would look almost familiar if you could stand in them, except what flows through them is not water. It is liquid methane. The Cassini spacecraft, operated jointly by the National Aeronautics and Space Administration and the European Space Agency, spent 13 years in the Saturnian system and mapped Titan's surface hydrocarbon cycle in extraordinary detail before its mission ended in 2017. What it found was a world running a nearly perfect parallel of Earth's water cycle, with methane in the role water plays here. Methane evaporates from the surface lakes, rises into the atmosphere, condenses, and falls back as rain. The largest lake, Kraken Mare, spans approximately 400,000 square kilometers, larger than the Caspian Sea. The second largest, Ligea Mare, contains an estimated 9 times 10 to the 4 cubic kilometers of liquid methane. These are not puddles, these are seas, and at the organic-rich shores where liquid methane meets the sediment, chemistry happens continuously. But here is where Titan separates itself from every other cold, distant world in the solar system. In 2004, the Huygens probe, released from Cassini and designed by the European Space Agency, descended through Titan's atmosphere for 2 hours and 27 minutes, transmitting data the entire way down. What it documented in that orange haze were complex nitrogen-bearing organic molecules called tholins. These molecules form when ultraviolet light from the sun interacts with the nitrogen and methane in Titan's upper atmosphere, creating chains of organic chemistry that rain continuously down onto the surface. Jonathan Lunin at Cornell University and Carl Sagan at the same institution decades earlier had both described Titan's atmosphere as a potential prebiotic chemistry laboratory, a place where the building blocks of life are being assembled in real time and then deposited onto a world with not one, but two potential liquid environments. The tholins are the detail that changes everything. In laboratory experiments conducted in 2008 and published in the journal Astrobiology by Sarah Hurst and colleagues, researchers mixed tholins with liquid water and found that the mixture spontaneously produced amino acids. Not after millions of years, in hours. The molecules that rain down onto Titan's surface and into its methane seas are the same class of molecules that, when briefly exposed to liquid water, begin organizing themselves into the structural components of proteins. Titan is not just wet. Titan is chemically primed. And 100 kilometers beneath the surface, it is also warm. Gravity data from Cassini, analyzed and published in 2012 in the journal Science, revealed that Titan's interior contains a subsurface ocean of liquid water, likely mixed with ammonia, sitting between the ice shell and the rocky core. This ocean is not accessible from the surface. It is sealed, but it exists. Two entirely separate potential habitable zones, layered inside the same moon, separated by 100 kilometers of ice and a temperature gradient that drops from the near absolute zero surface down to liquid water conditions in the dark below. The standard cosmological model for habitability says that liquid water is the critical variable, and that habitable zones around stars define where life is possible. Titan satisfies the subsurface water criterion while simultaneously hosting a completely different chemistry at the surface, one that researchers in prebiotic chemistry increasingly suggest may not require water at all. Methane-based metabolism is theoretically possible. Several astrophysicists, including Chris McKay at the National Aeronautics and Space Administration Ames Research Center, have proposed specific biosignatures that a methane-based organism on Titan's surface would produce, namely, a depletion of hydrogen near the surface and an absence of acetylene, both of which Cassini tentatively detected. But the mainstream model has no framework for life that uses methane as a solvent. It was not built for this. What does it mean when a moon hosts the conditions for two entirely separate origins of life simultaneously? If tholins become amino acids the moment liquid water touches them, and liquid water exists 100 kilometers below the surface, is that chemistry already happening in the deep? Is something in Kraken Mare metabolizing methane the way we metabolize oxygen, slowly, invisibly, at the edge of what instruments can detect? Does Titan need us to define what life is before it can answer whether it has any? That final question, whether our definitions are the limiting factor, not the universe's conditions, becomes even sharper when you look at a moon that should be geologically dead, frozen solid, and utterly unremarkable, and find that it is hiding an ocean no one can explain. Mimas, you are looking at a moon that should bore you. That is the honest truth of it. You have pulled up the Cassini spacecraft's image archive, the flybys from 2010, from 2015, and you are staring at a surface that looks like every textbook definition of a geologically dead world. Cratered, ancient, unchanged. The surface of Mimas is so densely packed with impact craters that geologists use it as a calibration tool, a baseline for counting collisions going back 4 billion years. Nothing has resurfaced it. Nothing has erased those craters. There is no volcanic smoothing, no tectonic reworking, no fresh terrain of any kind. The ice is old. The scars are old. The whole moon looks like it stopped happening billions of years ago. And then, in February of 2024, a paper was published in the journal Nature, and Mimas became one of the most disorienting objects in the solar system. The research was led by Valérie Laney, a planetary scientist at the Observatoire de Paris and the Jet Propulsion Laboratory, working as part of a team that had spent years analyzing the subtle gravitational signatures embedded in Cassini's orbital data. Cassini, which operated from 2004 until its deliberate plunge into Saturn's atmosphere in 2017, had measured the libration of Mimas, the tiny, rhythmic wobble of a moon as it moves along its orbit. Libration is a mechanical signal. The way a moon wobbles tells you something about what is happening inside it. A solid, frozen body wobbles in one way. A body with a liquid interior, a body with a hidden ocean, wobbles in another. Mimas wobbles the wrong way for a frozen body. The libration values extracted from Cassini's data were inconsistent with a solid interior. Laney's team modeled the gravitational data against every possible internal structure: solid ice, rocky core variations, different density distributions. The only model that fit the wobble was a body with a global liquid water ocean sitting beneath an outer ice shell estimated to be between 20 and 30 kilometers thick. The ocean itself, the models suggest, may be relatively young in geological terms, somewhere between 5 million and 15 million years old, which means it formed long after the surface of Mimas was already ancient and cratered and silent. Here is what makes this impossible. Every moon we have ever associated with a subsurface ocean has given itself away. Europa has surface fractures and active resurfacing. Enceladus erupts geysers of water vapor from its south pole, venting directly into space. Titan has atmospheric chemistry that points inward. Ganymede has a magnetic field that speaks to something dynamic beneath its crust. Even Triton, orbiting Neptune at the cold edge of the solar system, shows surface disruption consistent with internal processes. There is always a signal. There is always a leak. Some kind of energy escaping, some kind of geology whispering that something warm is happening below. Mimas has none of this. The surface temperature of Mimas sits at approximately 64 Kelvin, negative 209 degrees Celsius, and it is uniform. There are no anomalous warm patches. There are no fractures through which pressurized water might vent. There are no plumes. There are no regions of younger, smoother ice that would indicate upwelling from below. The surface is, in every observable way, the surface of a frozen, inert rock that has done nothing for billions of years. The largest feature on the entire moon is Herschel Crater, a 130-kilometer-wide impact scar, so enormous it nearly shattered Mimas entirely when it formed, giving the moon an accidental resemblance to a fictional space station. And even that crater, which should have produced regional geological disruption, sits there ancient and undisturbed. The standard cosmological model, or rather, the standard planetary science model, says that subsurface oceans are maintained by tidal heating, the flexing and compression of a moon's interior as it is pulled by a planet's gravity. Saturn is an enormous gravitational engine, and Mimas does sit in a somewhat eccentric orbit, which should generate some tidal friction. The model says this friction, over millions of years, may have been sufficient to melt a layer of ice in the deep interior and maintain it as liquid. But the model cannot explain the silence. Some astrophysicists and planetary scientists suggest that the ice shell of Mimas is so thick and so mechanically rigid that it is effectively decoupled from the ocean beneath it, that the liquid world below and the frozen world above have almost no communication with each other, no exchange of heat, no geological conversation, no escape route for whatever energy exists within. The shell, in this view, is not just thick, it is a perfect seal. The ocean is not leaking because it cannot leak, which raises a question that planetary science has not fully settled. If an ocean can exist in total silence, with no surface expression, with no heat signature, with no geological activity whatsoever, how many other moons are we looking at right now, dismissing as dead while something liquid waits beneath? What does life need, at minimum? Does it need geological activity? Does it need a surface signal to confirm its own existence? Or can it sit in the dark, beneath 30 kilometers of ancient ice, in an ocean that formed 15 million years ago, in complete and total silence? And if it is there, would we ever know? From a moon that hides everything behind an unblemished face, we turn now to a world that cannot hide what it is: Ganymede, the largest moon in the solar system, a body so substantial it carries its own magnetic field and shelters the deepest ocean we have yet confirmed anywhere beyond Earth. Ganymede. You are standing in front of the wrong mental model. That's the only way to describe the feeling when you actually sit with the numbers. You've been thinking of Ganymede as a moon, a satellite, a rock in orbit around Jupiter. Adjust that. Adjust it now. Ganymede has a diameter of 5,268 kilometers. Mercury, a full planet, the innermost world in the solar system, a body that has orbited the sun for 4.6 billion years, has a diameter of 4,879 kilometers. Ganymede is larger, not slightly, not marginally, larger by 389 kilometers. If you ripped Ganymede out of Jupiter's gravitational grip and placed it in a direct orbit around the Sun, every classification system in planetary science would call it a planet without hesitation. It is, by every physical measure except orbital independence, a world. And it may be a world that is alive. The Hubble Space Telescope made the observation that changed everything on March 18, 2015, when a team led by Joachim Sauer of the University of Cologne published results in the Journal of Geophysical Research, Space Physics, that rewrote what we thought we knew about Ganymede's interior. Sauer's team had been watching the moon's auroral bands, ribbons of glowing plasma that appear at Ganymede's poles, created by the interaction between the moon's own magnetic field and Jupiter's vastly more powerful one. The technique was elegant in its simplicity. Rock a saltwater ocean back and forth inside a magnetic field, and that ocean will generate its own electromagnetic signal. The auroral bands will wobble. The wobble will be measurable. The team compared what the wobble should look like if Ganymede's interior were dry rock against what it should look like if a deep, electrically conductive saltwater ocean existed beneath the surface. The wobble they observed was just 2 degrees of arc. Without an ocean, it would have been 6 degrees. The difference between those two numbers is a subsurface ocean estimated to contain more liquid water than all of Earth's oceans combined, by a factor of more than 25. But the scale of that ocean is where the mind begins to genuinely struggle. 800 kilometers deep. Stand on the surface of Earth and dig straight down. At approximately 30 kilometers, you will have passed through the entire crust. At 2,900 kilometers, you reach the boundary between the mantle and the outer core. Ganymede's ocean, at 800 kilometers, doesn't fit inside any frame of reference we intuitively possess. And because that ocean is so profoundly deep, the pressure at its base becomes extraordinary, sufficient to compress water into exotic high-pressure crystalline phases of ice, structures known as Ice 6 and Ice 7, forms that do not exist under any conditions found naturally on Earth's surface. The bottom of Ganymede's ocean is not liquid. It is a strange, dense, compressed ice that nonetheless exists within what is technically still a body of water above it. The ocean doesn't simply sit on rock, it sits on physics. Here's what makes this doubly impossible. Ganymede generates its own magnetic field. It is the only moon in the solar system known to do so. The magnetic field has a strength of approximately 719 nanoteslas at its equator, weak compared to Earth, but measurable, structured, real. A magnetic field of this kind requires, under current geophysical models, a liquid, electrically conductive interior that is actively convecting, a dynamo. Something inside Ganymede is moving, generating, sustaining a planetary-scale electromagnetic structure that has persisted for timescales we cannot yet pin down. The standard cosmological model, or rather, the standard model of planetary habitability, holds that life requires liquid water, a source of energy, and the presence of relevant chemical compounds. Ganymede satisfies the first condition extravagantly. The energy question is where the current consensus focuses its attention, pointing to tidal heating from Jupiter's gravitational influence and residual radiogenic decay within the moon's rocky mantle as plausible heat sources sufficient to maintain liquid water at depth. The chemical inventory, while not yet directly sampled, is expected to include salts, sulfur compounds, and possibly organics delivered by billions of years of cometary and meteoritic impact. But the standard model struggles with the geometry. If the ocean floor is sealed by high-pressure ice, what pathway exists for nutrients and chemical energy from the rocky mantle below to reach the liquid water above? On Enceladus, hydrothermal vents appear to interact directly with a liquid ocean. On Ganymede, that ice layer at the base may form a barrier, thermal, chemical, physical, between the potential chemistry of the mantle and the water above it. Some astrophysicists suggest that localized melting, convective upwelling, or fracturing in the basal ice layer could maintain exchange. A minority of researchers propose that the magnetic field itself indicates enough internal heat to create dynamic interaction at the rock-ocean boundary. Neither position is confirmed. Neither position is eliminated. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, launched in April of 2023 and is projected to enter Ganymede orbit in 2034. It will be the first spacecraft ever to orbit a moon other than our own. It will carry magnetometers, ice-penetrating radar, and particle detectors. It will begin to answer these questions with data rather than inference. But until then, ask what you cannot yet answer. What is happening at the base of 800 kilometers of ocean? Does the magnetic field that makes Ganymede unique also make it hospitable? What chemistry has been running in that darkness for 4 billion years? Is the ice at the bottom a floor or a lid? And if it is a lid, what does something pressed against the underside of a lid do, given enough time? The answer to that question may not stay inside Jupiter's system. Neptune's largest moon, Triton, orbits its planet backwards, and what lies beneath its nitrogen-frosted surface may be the most improbable ocean story in the entire solar system. Triton. You are watching a moon die in slow motion. Not violently, not yet. The process is quiet, measured, spread across timescales that make human civilization look like a camera flash. You are standing inside the Voyager 2 Mission Control Center at the Jet Propulsion Laboratory in Pasadena, California. It is August 25, 1989. On the monitors in front of you, Neptune fills the frame for the first time in human history. Deep, unreachable blue, 4.4 billion kilometers from Earth. And there, sliding into view behind it, is Triton. The first thing the scientists notice is the direction. It is going the wrong way. Every major moon in the outer solar system orbits in the same direction its planet rotates. This is how moons form, from the same spinning disk of material that built their host planet, inheriting its angular momentum like children inheriting a gate. Triton does not do this. Triton orbits Neptune in the opposite direction, a retrograde path so fundamentally at odds with the physics of formation that the conclusion is almost immediate. This moon was not born here. It came from somewhere else. The standard cosmological model says that Triton is a captured Kuiper Belt object, a world that formed beyond Neptune in the cold outer disk of the early solar system, wandered too close to the gas giant, and was gravitationally seized before it could escape. This is a legitimate and well-supported hypothesis. The size matches, the composition matches, the reddish surface tints, the nitrogen and methane ices. These are the fingerprints of a Kuiper Belt body, the same class of world as Pluto, which Triton actually resembles closely in mass and diameter. Triton is approximately 2,700 kilometers across. Pluto is approximately 2,377. They are cosmically speaking almost twins, except one of them was kidnapped by a planet. But the capture created a problem that has never gone away. When Triton was pulled into Neptune's gravity, the orbit would have been wildly elliptical, a long looping path that brought the moon screaming close to Neptune and then flung it back out into the dark. Over hundreds of millions of years, tidal friction and gravitational interactions circularized the orbit. The moon settled, but the settling was not free. All of that orbital energy went somewhere. It went into heat, and that heat, generated deep inside Triton as the moon was gravitationally kneaded and compressed during the circularization process, may have been enough to maintain a liquid ocean beneath the surface for a very long time. Here is what makes this extraordinary. Triton exists in one of the coldest environments in the solar system. Its surface temperature sits at approximately 38 Kelvin, minus 235 degrees Celsius. It is the coldest measured surface of any object the Voyager mission encountered. In terms of raw temperature, Triton makes Europa look tropical. And yet, Voyager 2's cameras captured something that should not have been possible at that temperature: active geysers. Dark plumes of nitrogen gas erupting from the surface, rising approximately 8 kilometers into the thin atmosphere before being carried downwind in long, dark streaks visible across the pinkish southern polar cap. Active geology on a world that cold. The geysers were documented and analyzed in detail by the Voyager Imaging Science Team, led by Bradford Smith, with results published across multiple papers in the journal Science in 1989 and 1990. The eruptions are driven, the mainstream explanation holds, by solar heating, sunlight penetrating the transparent nitrogen ice, warming darker subsurface material, vaporizing trapped nitrogen gas until pressure breaks through the surface. It is a mechanism sometimes called a solid-state greenhouse effect, and it is scientifically reasonable. But some planetary scientists, including researchers who have continued studying Triton's thermal profile in the decades since Voyager, note that solar heating alone at Triton's distance from the Sun, roughly 30 astronomical units, may be insufficient to fully account for the energy observed. A minority of researchers propose that internal heat, the residual warmth left over from the violence of Triton's capture and orbital circularization, may still be contributing. If that internal heat persists, and if the models developed by researchers, including William McKinnon at Washington University in St. Louis, hold under scrutiny, then a subsurface liquid water ocean, kept from freezing by that same tidal energy, may exist beneath Triton's frozen crust today. And here is the dimension of this that stops you cold. Triton's orbit is decaying. The retrograde path creates tidal interactions with Neptune that are slowly, inevitably pulling the Moon inward. In approximately 3.6 billion years, Triton will cross the Roche limit, the threshold at which Neptune's tidal forces will exceed the gravitational cohesion holding the Moon together, and it will be torn apart. The debris will form a ring around Neptune, spectacular and silent. A moon with a possible ocean, active geysers, and a confirmed expiration date written into the physics of its own orbit. What has lived in that ocean during the billions of years the heat persisted? What is living there now, if the ocean remains? If life began in Triton's subsurface waters during the long, warm aftermath of its capture, where does it go when the Moon is destroyed? Does it scatter into space, frozen into debris? Can life survive that? And if Triton was once a Kuiper Belt object, one of countless billions of such bodies orbiting the outer edges of star systems across the galaxy, how many of those distant, frozen worlds are quietly warm inside and quietly alive? Callisto offers a different kind of silence, an ancient one, carved not by a dying orbit, but by the sheer, undisturbed depth of geological time. Callisto, you are reading a printout, that's all. No flashing alerts, no crowded control room, no moment of sudden revelation. Just a quiet office somewhere inside the Jet Propulsion Laboratory in Pasadena, California, sometime in the late 1990s, and a sheaf of magnetometer data from a spacecraft called Galileo that has been threading its way through the Jovian system for years. The numbers look routine at first, then they don't. The magnetic field readings near Callisto are varying in a way that requires a conductor. Something beneath the surface of this moon is responding to Jupiter's rotating magnetic field. Something is moving. Something, by the logic encoded in Maxwell's equations, must be liquid. You set the printout down. You pick it up again. The moon you are looking at is the most battered object in the entire solar system. It has been geologically dead for billions of years. It has no volcanism, no tectonic activity, no measurable internal heat. And yet the data is telling you there is an ocean inside it. Here's what makes this impossible. Callisto is the outermost of Jupiter's 4 Galilean moons, orbiting at a mean distance of approximately 1.88 million kilometers from Jupiter, completing one circuit every 16.7 days. That orbit is nearly perfectly circular, an eccentricity of just 0.0074, and that circularity is the entire problem. Tidal heating, the mechanism that keeps Europa's ocean liquid and powers Io's volcanism, is generated by the gravitational flexing of a moon's interior as it moves along an elliptical path, alternately pulled closer to and pushed farther from its host planet. The more eccentric the orbit, the more flexing, the more heat. Callisto's orbit generates almost none of this. The tidal dissipation rate inside Callisto is estimated to be somewhere between negligible and essentially zero. The moon, by every thermal model available, should be frozen through. The Galileo spacecraft, operated by the National Aeronautics and Space Administration and active in the Jovian system from December 1995 through September 2003, made multiple close flybys of Callisto. During those passes, its magnetometer detected clear perturbations in Jupiter's background magnetic field, perturbations consistent with electromagnetic induction inside Callisto. The inference, drawn and published by Margaret Kivelson and her team at the University of California, Los Angeles, in papers appearing in the Journal of Geophysical Research around 2001 and 2002, is that a layer of electrically conducting fluid exists somewhere beneath Callisto's surface. A saltwater ocean. The induced magnetic signal implies this layer sits within a few hundred kilometers of the surface, likely beneath an ice shell estimated at 80 to 150 kilometers thick. The ocean itself may extend as deep as 10 kilometers or more. The surface above this inferred ocean is ancient beyond comprehension. Callisto's crust is saturated with craters. Every square kilometer of its visible face bears the record of 4 billion years of impact history, untouched by any resurfacing process. There are craters inside craters inside craters. Multi-ring impact basins like Valhalla, measuring roughly 1,850 kilometers across, stare outward from the surface like geological fossils. This is a world that has done nothing since its formation. No heat from below has ever risen to erase the record above. And yet, below that archive of stillness, something is liquid. The standard cosmological model, or more precisely, the standard planetary science model for icy moon interiors, says that radioactive decay of elements like uranium, thorium, and potassium within Callisto's rocky component may be sufficient to maintain liquid water when combined with the slight insulating effect of the ice shell above. Radiogenic heating alone, the argument goes, could plausibly keep a subsurface brine from solidifying entirely, particularly if the water contains dissolved salts or ammonia that lower its freezing point. This is a reasonable mechanism. It has precedent in planetary science. It does not require anything exotic. But the thermal models that invoke radiogenic heating alone struggle to produce enough sustained warmth over the full age of the solar system to maintain the ocean at the depth and extent that the magnetic data implies. Callisto is not small. Its radius is approximately 2,410 kilometers, comparable to Mercury, but its rock fraction is insufficient, according to most interior models, to generate the heat flux that a robust liquid layer would seem to require. Some astrophysicists suggest that Callisto's interior may be only partially differentiated, meaning rock and ice remain somewhat mixed rather than fully separated into distinct layers, which could alter heat distribution in ways not fully captured by current models. A minority of researchers propose that the magnetic signal itself may be partially explained by magnetized materials in the crust, rather than purely by induction, which would reduce the required ocean volume, but not eliminate it. The ocean, if it exists, sits inside a world with no apparent reason to have one. What is generating enough heat to keep water liquid inside a geologically dead moon for 4 billion years? If radiogenic decay is truly sufficient, why does the thermal modeling consistently fall short? What does life, if it is anywhere in that darkness below Callisto's cratered face, use as an energy source when there are no hydrothermal vents, no tidal flexing, no geological engine driving chemistry? Is the silence of Callisto's surface a mask, or is it the whole truth? And if an ocean can persist here, without tidal heating, without volcanism, without any of the mechanisms we assumed were necessary, how many other frozen worlds are we dismissing too quickly? The question of hidden oceans in impossible places does not end at Callisto. It drifts outward in the solar system, all the way to Saturn, where a moon called Titan holds a different kind of mystery in the very chemistry of its air. Titan's atmospheric hydrogen depletion. You are not looking for life. That is the thing to understand before any of this begins. You are running a chemical inventory. You are a planetary scientist with access to data returned by the Cassini spacecraft, and your job is atmospheric accounting, cataloging what molecules are present, in what concentrations, and where they move. It is painstaking work. It is not glamorous. You are not hunting for organisms. You are filling in columns on a spreadsheet of a world, and then a column comes back empty. Hydrogen, molecular hydrogen, flowing downward through Titan's thick orange atmosphere toward the surface. Flowing down, and then, according to the data, simply stopping, not accumulating, not reflecting back upward, not detectable at the surface at all. You check the numbers, you check them again, you run the atmospheric chemistry models. The models say the hydrogen should be there. The data says it is not. Somewhere between the atmosphere and the ground of a moon, 1.2 billion kilometers from Earth, something is consuming hydrogen, and you don't know what. This is the moment the spreadsheet becomes something else entirely. The Cassini-Huygens mission, a joint collaboration between the National Aeronautics and Space Administration, the European Space Agency, and the Italian Space Agency, arrived at the Saturnian system in 2004 and spent 13 years mapping, probing, and analyzing everything within reach. Titan was a primary target. with a diameter of 5,150 kilometers, larger than the planet Mercury, and a nitrogen-rich atmosphere 1.5 times denser than Earth's at sea level, Titan was understood to be the most Earth-like body in the outer solar system. It has weather, it has seasons, it has rivers and lakes and rain, though none of it is water. The lakes of Titan are liquid methane and ethane, pooled across a surface so cold, approximately 94 Kelvin, which is negative 179 degrees Celsius, that water ice behaves as bedrock. In 2010, 2 separate analyses of Cassini data were published, and together they outlined something that the atmospheric chemistry models of Titan could not cleanly absorb. The first, led by Daryl Strobel of Johns Hopkins University and published in the journal Icarus, modeled the flow of molecular hydrogen through Titan's atmosphere and found a net flux of hydrogen toward the surface at a rate of roughly 10,000 trillion molecules per second. The hydrogen was going down. It was not coming back. Strobel himself was careful, describing the finding as a chemical anomaly requiring explanation rather than a biological discovery. But the implication lived in the gap between what the data showed and what the chemistry could account for. The second analysis, led by Roger Clark of the United States Geological Survey and also published in 2010, examined Cassini's visual and infrared mapping spectrometer data and found that acetylene, a hydrocarbon that ultraviolet radiation from the sun should be producing continuously in Titan's upper atmosphere and raining down onto the surface, was also essentially absent at the surface level. Acetylene should be there. The photochemistry demands it. It is not there. Here is why astrobiologists noticed. In 2005, Chris McKay of the National Aeronautics and Space Administration's Ames Research Center and Heather Smith of the International Space University published a theoretical paper proposing that if methanogenic life existed on Titan, organisms that breathed hydrogen instead of oxygen and consumed acetylene as an energy source, the way Earth life consumes glucose, the chemical signature of that life would look exactly like this. Hydrogen depletion at the surface. Acetylene absence. Not as proof of life, as a predicted signature, a fingerprint written before the crime. The standard cosmological model of Titan's surface chemistry says that non-biological processes are almost certainly sufficient to explain both anomalies. Hydrogen can be absorbed into the water ice and hydrocarbon bedrock of the surface through purely physical processes. Acetylene may be converted into other compounds through catalytic reactions with minerals or by ultraviolet processing before it reaches the ground. Titan's chemistry is extraordinarily complex. It produces hundreds of organic compounds in its atmosphere, and the absence of any single molecule does not require biology to explain it. Planetary scientists are right to apply this caution. The history of astrobiology is full of premature conclusions, but the caution cannot fully close the gap. What the non-biological explanations have not yet produced is a specific, testable mechanism that accounts for the magnitude of the hydrogen flux disappearance and the acetylene absence simultaneously, on the surface, at the observed rates, without invoking processes that themselves require further confirmation. The two anomalies appear independently but point in the same direction. That directional consistency is what makes planetary chemists uncomfortable in ways they rarely say out loud. Titan's surface, beneath those orange clouds, sits at the edge of a chemical story that is either almost entirely mundane or almost entirely extraordinary, and the data does not yet let us know which. What consumes hydrogen on a world where nothing should be consuming it? Why is acetylene, a molecule the atmosphere manufactures constantly, absent precisely where it should accumulate? If life on Titan breathes hydrogen and eats acetylene, what else might it be doing that we haven't thought to look for? And what does it mean that the predicted chemical signature of life appeared in the data before we ever landed on the surface to look? Saturn's moon system does not run short of mysteries, and the next one arrives not in orange haze and methane seas, but on Dione, a world of fractured ice and unexpected oxygen, orbiting in silence just beyond the rings. Dione. You are standing at a console inside the Cassini spacecraft's Instrument Operations Center at the Jet Propulsion Laboratory in Pasadena, California. The year is 2015. The data arriving on your screen's quiet, understated. It doesn't scream at you the way some discoveries do. There's no eruption plume, no kilometer-high geyser, no surface chemistry glowing in the infrared. What you're looking at is a thin haze of signal, barely a whisper against the noise floor. and it shouldn't be there at all. You check the calibration. You check the source. The Cassini plasma spectrometer is reading molecular oxygen ions in the space directly surrounding a moon that by every reasonable expectation should have nothing surrounding it at all. The moon is Dione. It is a body roughly 1,123 kilometers in diameter, composed primarily of water ice wrapped around a small rocky core, orbiting Saturn at a distance of approximately 377,000 kilometers, sitting comfortably in the planet's magnetosphere, bathed in radiation, and producing oxygen. Quietly, continuously, with no fanfare and almost no attention from the broader scientific community. Here's what makes this remarkable. Dione is not Europa. It is not Enceladus. It generates no headlines. The Cassini mission, which spent 13 years in the Saturnian system between 2004 and 2017, made hundreds of close flybys of the more dramatic moons and returned comparatively few dedicated passes of Dione. The scientific literature reflects this imbalance. And yet what little data Cassini did collect has produced findings that on any other moon would have triggered a second mission within a decade. The oxygen exosphere was documented in a 2012 paper published in Geophysical Research Letters by researchers Andrew Coates and colleagues at University College London's Mullard Space Science Laboratory. The detection came from the Cassini plasma spectrometer and the ion and neutral mass spectrometer instruments. What they found was a surface density of approximately 90,000 oxygen molecules per cubic centimeter, an extraordinarily thin atmosphere by Earth standards, but an atmosphere nonetheless. The mechanism driving it is radiolysis. High-energy particles trapped in Saturn's magnetic field continuously bombard Dione's icy surface, breaking the molecular bonds of water ice and liberating individual oxygen molecules into the space above the surface. The same process has been observed at Europa and Ganymede. What is different at Dione is what the magnetic field is doing. Saturn's magnetic field lines do not simply pass through Dione's vicinity unchanged. They interact with it. The Cassini magnetometer detected disturbances in the local magnetic field during close flybys. Specifically, the kind of perturbations produced when a moon is not merely a passive rock inside a magnetic environment, but is actively injecting charged particles into that environment. This is the behavior of a world with internal activity. A world with something conducting beneath its surface, something liquid. The standard cosmological model, or rather, the standard planetary science model for icy moons, says that Dione's interior was likely geologically active in the distant past, heated by tidal interactions with Saturn and neighboring moons, and has since cooled to a largely inert state. The surface geology partially supports this. Cassini's imaging revealed ancient tectonic features, long cliff-like scarps called chasmata, grabens, and fractured terrain that suggest a history of internal stress and deformation. The mainstream interpretation holds that these are relics, a geological record of past activity now frozen in place, with the magnetic anomalies explainable by remnant magnetization in the crust or by interaction effects that don't require a liquid interior. But the magnetic field data doesn't fit this cleanly. Researchers including Attilio Rivaldini at the Royal Observatory of Belgium, working from Cassini's gravity measurements published in the journal Icarus, in 2019, found that Dione's moment of inertia, the measure of how its mass is distributed from core to surface, is consistent with differentiation, a separated interior, a rocky core, and potentially a layer of liquid water between that core and the overlying ice shell. The model suggests this subsurface ocean, if it exists, could sit roughly 100 kilometers below the surface. Not a global ocean necessarily, but a persistent reservoir. And if that reservoir is in contact with the rocky core beneath it, the chemistry available, minerals, heat flux, water, the radiation-generated oxygen cycling from the surface above, begins to form a profile that researchers who study habitability cannot comfortably dismiss. The reason Dione remains obscure is almost administrative. Mission priorities in the Saturnian system were set before Cassini arrived, and Enceladus's erupting plumes rightfully commanded attention. Dione had no such dramatic calling card. It offered instead a quiet signal, a whisper in the plasma data, an oxygen reading that should not have been there, above a moon that should not warrant a second look, orbiting a planet 446 million miles from the Sun where life has no business existing at all. What else is Dione producing that no instrument has yet been close enough to detect? If there is liquid water 100 kilometers down, what chemistry is occurring at the boundary between that water and the rock below? How many other moons in this solar system are we ignoring because they lack the spectacle to demand our attention? And what does it mean that oxygen, the molecule most associated with biological processes on Earth, is being continuously generated on a world that almost no one is watching? Dione's silence may be the loudest thing about it, and out at Uranus, a moon called Titania has been keeping its own silence for nearly 4 decades. Titania, you are standing at the edge of something that should not be there, not metaphorically. The canyon beneath you. If you were standing on the surface of Titania, in the pale, slanted light of a sun so distant it appears as little more than a bright star, drops away into darkness for depths that instruments have only approximated. It stretches to your left and to your right until it disappears beyond the curve of a world smaller than Earth's moon. 1,500 kilometers of fractured crust, a scar so long it would span the entire continental United States from coast to coast, carved not by water, not by impact, not by tectonic collision, but by the moon itself expanding from the inside out. The ground beneath you cracked open because something inside pushed. The question that has followed Titania since Voyager 2 swept past it on January 24, 1986, is simple and uncomfortable. What is still pushing? Voyager 2 remains the only spacecraft in human history to have visited the Uranian system. It passed within 579,000 kilometers of Uranus and captured imagery of Titania at a resolution that revealed, briefly, incompletely, tantalizingly, a surface defined by contradiction. Ancient cratered highlands sitting directly adjacent to smooth, geologically young terrain, fault scarps. Grabens, the kind of surface geology that, on Earth, would indicate ongoing interior activity. Voyager 2's flyby lasted hours. Its imaging window over Titania was shorter still. Scientists have spent nearly 4 decades attempting to understand a world they observed for less time than it takes to watch a film. What they have reconstructed, through decades of thermal modeling and compositional inference, is a portrait of a moon that refuses to be as dead as its distance suggests it should be. Titania is 1.578 million kilometers from Uranus. It orbits in a system that sits 2.72 billion kilometers from the Sun. At that remove, the solar input is negligible, roughly 360 times weaker than what Earth receives. Surface temperatures on Titania drop to approximately 60 to 70 Kelvin in the sunless regions. By every intuitive measure, this should be a frozen, inert body. No tidal flexing of any significance, no meaningful radiogenic heating, no reason whatsoever for liquid water. And yet the models say something different about what lies beneath. The interior composition of Titania is estimated to be roughly half rock and half ice by mass, with a density of 1,711 kilograms per cubic meter, dense enough to suggest a differentiated body, one that separated into a rocky core and an icy mantle during its formation. Research published by planetary scientists, including work developed in the context of modeling Uranian satellites, most notably the thermal evolution studies associated with researchers like Linnea Quick at the National Aeronautics and Space Administration Goddard Space Flight Center, along with broader work from teams at the Lunar and Planetary Institute, proposes that the presence of ammonia changes the entire equation. Ammonia is not exotic. It is one of the most common nitrogen-bearing compounds in the outer solar system, and when it mixes with water, it functions as a powerful antifreeze. A water-ammonia mixture, at a concentration of roughly 30% ammonia by weight, does not freeze at 273 Kelvin, the way pure water does. It remains liquid down to approximately 176 Kelvin. 176 Kelvin is minus 97 degrees Celsius. It is a temperature so cold that it would kill any unprotected human being in seconds. And it may be warm enough, by the logic of this moon, to sustain a liquid ocean beneath Titania's ice shell today. The standard cosmological model, and the standard framework for assessing habitability in the outer solar system, does not place Titania high on the candidate list. The mainstream scientific consensus acknowledges the antifreeze hypothesis, but notes that the thermal models carry significant uncertainty. Without a heat source sufficient to maintain even ammonia-laced water in a liquid state over geological timescales, the ocean, if it ever existed, should have frozen. The radiogenic heating from Titania's rocky core was strongest early in the moon's history and has been diminishing for 4.5 billion years. The tidal forces from Uranus are weak. The energy budget, in the conventional accounting, does not balance in favor of persistence. But the fault canyons don't care about the accounting. Those grabens, those 1,500-kilometer rifts splitting Titania's crust, require expansion. Interior expansion of a body at this scale and age requires interior change. Something inside Titania changed after the surface had already cooled enough to crack. Some astrophysicists suggest that the refreezing of an internal ocean, slowly over billions of years, could produce exactly this kind of expansion, because water expands as it freezes, which means the surface record may be documenting not a living ocean, but a dying one, or one that is dying very, very slowly. Slowly enough that some liquid pocket, insulated, ammonia-laced, tucked against the rocky core, persists even now. If ammonia is there in sufficient quantity, the ocean lives. If it is not, it does not. One chemical compound. That is the entire margin. What was inside Titania when those canyons opened? What is still inside it now? If an ocean persists in darkness, 4.5 billion years old, at 176 Kelvin, in ammonia-laced water no instrument has ever reached, what has had time to begin? If life found a way in that ocean, would we ever build something capable of knowing it? The 10 moons are behind us now, and what they share is more unsettling than what separates them. What these 10 worlds are telling us, collectively, is not that life might exist somewhere else in the solar system. That framing is already too small. What they are telling us is that we built our models of habitability around the only example of life we have ever found, and then we went looking for copies of it, and then the moons of the outer solar system started returning data that didn't fit the template at all. Liquid water beneath kilometers of ice, nitrogen winds sculpting dunes of organic material, hydrogen being consumed from the atmosphere of a moon whose surface temperature sits at 94 Kelvin, magnetic fields generated by oceans that have never seen sunlight, plumes of salt water erupting into vacuum at temperatures that should make liquid anything impossible. The universe did not consult our models before building these places. And perhaps that is the deepest implication of everything documented here. Not that life is common, not that we are close to finding it, but that the conditions we assumed were prerequisites for life may be descriptions of only one narrow pathway through a space of possibilities that is almost certainly vast beyond our current comprehension. Enceladus has been active for potentially billions of years, longer than complex life has existed on Earth, and we did not predict it. Titan has a chemistry that resembles a prebiotic Earth in cold storage, and we did not predict it. Mimas looks dead from every instrument we aimed at it, and then revealed a liquid ocean anyway, and we did not predict that either. Each entry in this catalog is not an anomaly. Each one is a correction. The universe is not confirming our frameworks. It is quietly, methodically dismantling them. 10 moons. Each one a world. Each one holding something that shouldn't be there, according to the science that preceded its discovery. And beyond these 10, there are more than 200 known moons in this solar system alone, most of them unvisited, most of them unimaged at resolution high enough to reveal what lies beneath. And beyond this solar system, there are hundreds of billions of others, each with their own planets, their own moons, their own oceans hidden under their own ice, their own atmospheric signatures that no telescope has yet split into its component wavelengths. The universe offers no answers, only signals, and we are only just beginning to learn how to listen.